I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University.
Hi, I'm Angela Edwards. I'm a chemistry instructor at Arizona State University.
So last semester, we co-instructed BCH 341, the online edition, physical chemistry with a biological focus. And this semester, I'm using Yellow Dig as well. And I'm trying to use it and ask more and more polling questions to kind of get students engaged in really conceptually understanding the material as well as practically working a thing. And one thing we did, which is, this is a table out of Tinoco's book. So 5th edition, chapter 2, table 2.2, which is just very common physical properties of water, okay? And so one of the things, and I think I put it over here, but just to summarize, most of these you look through and you think normal properties, but there's a huge table here in the middle, right? And it's liquid water properties. So just starting with the thing, density, how it changes with temperature over the range where water is stable from 0 degrees Celsius to 100. What its surface tension, how its vapor pressure, it gets to, 1 atmosphere at 100, that's kind of expected. How its heat capacity changes, and, for the most part, it doesn't change much over liquid range. How its viscosity changes, surprisingly changes a lot, But I had him focus on this one because this one, I think, conceptually, kind of goes a lot of different directions for students, which is how does the enthalpy of vaporization change at temperature? Because they're used to just kind of one point, right? Like if you see the delta H of vape, it's rarely even, and it usually just gives a value. And if this was for water, you would make a very common assumption that what it was giving, and it would probably give 40.7 kilojoules per mole, that it's giving it to you at 100 degrees, right? Because that is the equilibrium boiling point of water at standard pressure 1 atmosphere, right?
All of these values are measured at standard pressure? All
of these are measured at standard pressure, which you're right, it doesn't, they should put an asterisk here and say, 1 atmosphere, pressure, because it would obviously, change. So, and they even, kind of give it here. But yeah, it's assuming everything's kind of at 1 atmosphere or atmospheric pressure here. So, that it has a large enthalpy of vaporization, given that it's at constant pressure, right? We often we substitute the word heat, right? A lot there. We often just say heat of vaporization because at constant pressure and assuming, everything else constant, that the enthalpy is the energy related directly to the heat term in this case. So it gets also interchangeably used. I think that confuses students a lot too. They'll say the heat of vaporization or the enthalpy of vaporization, and we should be more precise in our language a lot of times. But I think it's also important for students to recognize that these are common things that you see throughout the literature.
We do define in Gen Chem that the enthalpy is the heat at constant pressure, and they do learn about the heat capacity and how to derive heat from heat capacity or vice versa. So students should have at least some familiarity that the heat depends on the temperature, since it's equal to the mass times the specific heat, or the heat capacity times the temperature.
Right. And, and maybe they even have some type of intuitive feel that, while they all have the intuition that, you see the equilibrium boiling of water to vapor or steam at 100 degrees at atmospheric pressure, but they also have some intuition that water can vaporize at lower temperatures, right? We all have that experience that water will vaporize out of a cup or a blah, blah, blah in an open system. And while it's open, and therefore we're not saying it would do that in a closed system under equilibrium, you can vaporize water, at a lower temperature. And then the real question I asked him was just to try to get an intuitive feel for this. So why is it that it increases as temperature decreases? My gut feeling is they would have a natural intuition for that. If you're a little bit lower in temperature, to turn liquid water into vapor, that it takes more energy at low temperature shouldn't really surprise them too much, right? It probably already hits their natural intuition. But the one thing that might not be so obvious is this a linear change, or how is it changing with temperature? So that's why I really ask them to plot it. And so I plotted it here. And you'll be very familiar with this as well because of what we did last semester. I just used Google Sheets, right? And took those values, basically these values right here, and I did it in joules per mole, and then these temperatures, and I probably converted it to Kelvin, and made that plot there. So, and you can imagine why I did this in this specific way is because the slope is related to a heat capacity, and we usually think of the heat capacity in joule per kmol. So not in kilojoules per mole degree, C, right? So that's, in a sense, the reason. And I probably should have said that this was joule per mole instead of kilojoule, and I did put the K over here.
Well, I think that's why you can see that the heat capacity remains fairly constant, because it already has the temperature as one of the domains of the units, right?
Yeah, but you would say this, in a sense, really proves that, right? That the heat capacity over the entire liquid range remains constant. And this is where I would say students get most confused, because then the next question I ask them is, okay, you're right, like dH dt at constant P is a heat capacity. But the heat capacity of what? Because this is not the enthalpy of the liquid. This is not the enthalpy of the vapor. This is the enthalpy of the change between the two, right? So this heat capacity is really a delta, right? It's really the change. It's the change in the heat capacity between the vapor and the liquid.
That makes sense.
So it's really not saying that the heat capacity of the liquid is, constant. In fact, it's explicitly shown here. And it's not even shown to change linearly, right? Like it goes, down and then back up, so but that said, to first approximation, you could just say that it's 76 or 75.
It certainly varies less than the viscosity or
a
things
lot,
that have
a lot. So you'd say it's almost constant. To say it's constant is pretty accurate, to first approximation. But it's really looking, if the vapor changed in some weird way, then this might not, be so linear. So it's really a delta CP, because this is a delta H, here, that you're looking at the change in the delta H of vaporization. And so what I like to do, in fact, I think I did it even bigger here, is I like to do it graphically. And this is what I know you and I both last semester, tried to really point out to them, because maybe I internalized, but for me, just looking at numbers like this on a table and kind of rationalizing a few things helps a little, but what really helps me is really plotting it. And
having visual information.
It's
so helpful.
And Gibbs is famous for this. Like, Gibbs was famous for creating graphical methods for looking at thermodynamics. And so I guess I just kind of follow that model. And I like what the book did. This, again, comes directly out of Tinoco. You can see that they took the enthalpy, which you almost always need to look at as a delta, but they took it, as a standard state. So it's going to cross, because this is, so this is the standard molar enthalpy of the material. So it's right at, room temperature here is where it's going to cross zero and above and below. Now, like I said, we were mainly looking at this one, and we're used to it at, on this plot, it would be 373 or K or 100 C, and, like we said, we're 40.66 kilojoules per mole. So what it's really saying, is, what is, starting down here, what changes this slope from this slope from this slope is the heat capacity, right? CP, so CP of ice is less than water, is larger, and then steam is back down to about, so this is around 30 some, this is 75, this is 30 some again. So, what I like to think of it is you're still looking at this same delta. This is looking at it, this is the delta H of 40 at 100, but all this is doing is saying, let's extend this line a little bit. and it's assuming that the heat capacity stays the same, right? So we could do this really well. Unlike my poor drawing skills, we could. Whoa, it got really bad there.
Add a trend line to those data points over 373 on your actual computer.
Yeah, but this is where Google Sheets and stuff makes it much better, right? Like,
and in highlight those data points and add trend line.
And then it's very clear if you go to the other endpoint, which is to do it at 0 degrees Celsius or 273 Kelvin, which is where it ends at. And you look at it, well, this slope changed a lot more. This one changed a little. Right. So you can clearly see that delta H of vaporization, but now in its molar, is going to be a bigger value. And I think it was 44, right? And you can see that, and now you can really see the reason why. Is that it's because it's more because of this.
Right.
The higher heat capacity of the liquid than it is, because of that.
So what do we want students to relate this heat capacity to physically? And what I see when I look at this graph, most obviously, before you had extended the lines and added a new delta H of vaporization, is that the delta H of fusion is so much smaller than the delta H of vaporization. So certainly, since these heat capacities are phase dependent, and then these phase transitions, if you think about water specifically in an ice form, in some crystalline form, then you typically have about 6 interactions for each water, right? You have some hexagonal lattice structure. And then in the liquid state, there's an average of 3 or 4 intermolecular forces. These are some hydrogen bonds, where you can think of also, depending on if there's some pressure differentials or anything like that, then of course we also have, varying strengths of van der Waals forces underlying that and everything. Right. So the sum of those seems to obviously be a lot more to overcome to get into the gas phase. Once we want to vaporize something, you have to overcome all of those intermolecular forces rather than just removing 2 or 3 on average of them, which is what you do for the fusion, for the melting process. So is that what you want students to primarily get out of a graph like this, that they have a difference in intermolecular forces, they have more forces in between any vapor particles at a lower temperature that would cause them to condense more readily and go back to the water phase, go back to liquid water phase, and simultaneously more forces to overcome the cooler the temperature.
Right. Well, and also just to realize that it's really saying that in the gas phase, where things are typically fairly ideal, right? I mean, this is basically an ideal gas for the most part. So, I mean, in other words, it's at low pressure, 1 atmosphere. So if you calculated 1 atmosphere, water vapor, and asked how far apart the water molecules are, you would find that they're fairly far apart. They work fairly ideally.
Sure.
Obviously, they get less ideal as you go down in temperature. And I see where you're coming from. Like, yes, I think one of the things you can't help but to want to put to this macroscopic picture is the microscopic reasons why this has a higher heat capacity, why this has a lower one, what degrees of freedom allow it to store that energy, heat, and release it, etc. But I think there's also another really important one here, especially given that this is for biological students. So, and that is, think about in a lot of what you said, like a lot of biological systems, you can't boil things. Like, you don't boil a protein, you don't boil DNA, right? Hell, you can't even boil sugar. Try to take glucose and boil it. It turns very viscous and aggregates into oligomer chains. Like, a lot of things don't even come close to, when you up their temperature, chemistry takes over before the physical equilibria. Sure. Some chemical equilibrium and reaction happens, way before the physical equilibria of it being able to vaporize takes effect. So sometimes you can only observe the vapor pressure not at its Gibbs free energy point, because there it would be degraded and all sorts of other things would happen. It's only at these out of equilibrium places that you can actually get things like sugar to go into the gas phase and stuff like that and look at its heat. And I think the one thing they learn in freshman chemistry that is still just the most important, right, is Hess's law. Like, is
Sure.
that, yeah, you might not ever be able to get to this point. Now in water you can,
Right.
but if you know the heat capacity, if you were given it at some incredibly, low temperature where you could do it and it degraded up here, you can still, if you wanted to know that one, you can still just take, this, that, and that, and those three will equal, that other one. So you can still
Right.
always do something way over here and relate what it would be in some other point. And this is even true of what I would call simple systems. It's known as the Madeline energy in salts. Like try to vaporize salt, sodium chloride, right? Like it doesn't like to, because sodium doesn't like to separate from chlorine. And so
Right.
it's known as an extra Madeline energy, which should just be called Coulomb, right? That sodium chlorine likes to go out together.
Right.
It doesn't like to go out as individual, ions, et cetera. So there's a lot of things that you would say almost have zero vapor pressure or degrade before they have any significant et cetera. So I think there's a lot that biochemists, can get out of looking at this type of behavior.
So what we get from this graph is that it looks as though the delta H term, if it's a change in the enthalpy, that change in the enthalpy is usually temperature dependent. Are there any cases where you would have temperature independent values for enthalpy and entropy for a biological process? Yeah,
so very good point. Like, like you said, and I think you even alluded to it earlier, like, the other thing I think that's critical is realizing that you can estimate a lot of things. Like what's one of the most classic things we do? We have them start somewhere down here as ice and end somewhere up here at steam, and we
Right.
ask how much heat is required to do that. If you had 1 mole, 1 gram, 1 something,
Right.
You had a little thing of, a little cube of ice here and you wanted to turn it into, steam, how much energy does it take?
Right.
And you made a very good point. Like to first approximation, you could say this doesn't have any heat capacity, that it then melts and it doesn't have any heat capacity, and then it boils. And in a sense, you could just sum these two numbers and get pretty close, right? If you want to get a little closer, then you can take into account that yes, actually it does take a little bit of heat to go from ice at minus 50 degrees Celsius to, ice at 0 degrees.
Right.
But it doesn't take a lot. Where most of the heat goes into to get ice to steam is to first melt it and then boil it.
That's true. When we teach thermochemistry and Gen Chem, it tends to be usually some joules transferred when you use your Q equals M delta T CP equation versus some kilojoules of energy.
Or a better, another way of putting it is if you take this, this right here, that little term and that one, those two together go to the delta H of sublimation. If you were just to go directly there and not even take into account any of these heat capacities, right? In fact, we usually make that the delta H of sublimation is just those two, right? And doesn't account for, any heat in between, when obviously there is some, but like you said, then you can get even more. It's really about how precise do you want to be? If you want to be plus or minus 10%, and you're starting at ice and going to steam, you can just, take the delta H of fusion and vaporization, add them together, no matter where in temperature you are, and you're good. If you're really working with that water and you care very precisely about stuff, then yeah, you better take into account the heat capacities. And like you said, oftentimes to first approximation, we just assume they're constant.
Right.
That the heat capacity, is a function of is not a function of temperature over these ranges. But if you really want to get as accurately as possible, then you need to take into account the temperature dependence of the heat capacity at each one of these steps as well. And so I think of it as I tend to first estimate it just by taking the two and say, I'm going to get a number, about 40 plus 6. I'm going to get a 47, kilojoule per mole change here. And if I don't get something kind of in the ballpark of that, I know I did something drastically wrong. Then I take the linear dependence with the heat capacity because it's just easiest to integrate, CPDT than anything else. Then if I want to really get as precise as possible, then I take, the temperature dependence of the heat capacity, which usually goes as a series expansion, because obviously it's a little more cumbersome to integrate.
Sure. Why is that one nonlinear when it comes to being within a single phase, like the liquid water phase, and that one doesn't have an exact linear dependence? It's the only one that seemed to, at the very least, not have the trend of constantly increasing or decreasing.
Well, all of heat capacity goes back to how it goes into degrees. It goes to eventually what I would call molecular thermodynamics or statistical mechanics. It's looking at how the heat capacity changes with how it can store heat in different interactions, right? And like you said, whether it be London dispersion forces, hydrogen bonding, which is famous in water,
Sure.
It's rotational, vibrational degrees of freedom, et cetera, and how all of those independent molecular interactions change with temperature.
Right.
And some do so in very predictable ways. Very simple systems like argon have argon can't, famously rotate because it's spherical. It only
Right.
has London, dipole-induced dipole or dispersion type forces associated with it. So, but other things as they get more complicated, like water, how the hydrogen bonding changes is very dependent on the density as well as the energy you put in and a
Sure.
lot of other things. So how you change these different degrees of freedom can get very nonlinear very quickly in more complicated molecules.
So would you expect it to either be constantly increasing or decreasing, or just stay within an even smaller standard deviation for a system like argon in a liquid phase, if you made liquid argon?
Yeah, I mean, what you usually say is that usually most liquids stay pretty good because in their equilibrium range, it's usually not large enough. The liquid phase compared to, the huge ranges where you can make solids and gases or plasmas in a sense, is much larger in temperature pressure ranges than liquid. It's a very limited range.
Sure.
So a lot of things to first approximation end up pretty linear unless you go to kind of what I would call real extremes in pressure or temperature. In this case with water, it's if you supercool it in incredibly long ways, then it can, it won't stay like that at all. It will get very nonlinear very quickly. And, but this is at minus 20, 30, 40 degrees Celsius.
Sure.
And we're all familiar with supercooling water because your water never freezes at 0 degrees when you put it in your ice cube tray. It's always minus 3, minus 5, minus 10, before it freezes. But then, keep in mind, then it liberates heat. So then it can do some weird things. You can watch it then, start to warm back up.
So how does this transition what does this transition have to do with reversibility? You mentioned that when you heat a lot of biological systems that they denature, right? So we think of something like the melting transition, or certainly if you were to make a vapor transition of a protein, which would take a lot of effort.
Well, you'd say there's a whole field to that, right? Like
Right.
getting proteins or any biological macro in the gas phase,
Right.
Every mass spec person, you'd say that's what they spend their years doing. Most of it has to
Sure.
do with ionization processes, but it's getting it into a gaseous type phase, that kind of defines a lot of these things, and they
Sure.
do very, exotic tricks.
So does this temperature dependence have something to do with the reversibility? Because when I think of something like pure water, we know obviously that we can vaporize it or just recondense it back into water. So that makes this have only one plot on this graph. Would you expect to have some different values for a cooling process for a biological system that wouldn't overlap with the plot that we have shown here?
Well, I mean, the first thing you have to realize is if it's not able to get there because of a chemical reaction, then you move into chemical equilibria, and then you're not even talking about then boiling the same material, right? Like the number of moles just changed on you. But I bring it up not to be as a confusing point, but just to think of most biological systems we work with, that's the practicality of them. Very few of them boil,
Right.
right? Like, hell, most of them don't even melt, right? Like they
Right.
just solubilize in water and then crystallize out as a solid. Like, we have to be very careful that we look at these general phase equilibria of simple systems that classically undergo these three phases of matter.
Right.
But then we need to realize that most biological systems don't. And in fact, they go through completely different types of physical equilibria, like liquid crystal transitions.
That's exactly what I was about to ask. Yeah, so would you expect to see a similar trend then if instead of thinking about a melting process, we thought about, let's just say, a membrane where you have, some lipid raft or some sort of, heavy van der Waals interactions between these more saturated long hydrocarbon chains where you form a very rigid portion of the membrane, especially at lower temperatures. Would you expect you could then define, instead of delta H of vaporization, maybe just delta H of, I don't know, sub LC to liquid transition or something, right? Where you have put in some heat and you're able to, transition from these things being stacked together to more freely forming.
Yeah.
Would they exhibit the same phenomena where they would have a increase in the delta H term for that as you decrease the temperature?
Yeah, exactly. So, and you could plot it more or less the same way. You could say that, you have some, most people, like you said, would call it a gel phase at low temperature, and then it would have at higher temperature. Most people, they're usually liquid crystalline phases at high temperature, and then there's a kind of a delta H. It's often a little more smeared out than it is, exactly first order. So
Sure.
A lot of these aren't first order transitions, but that's kind of devil in the details. But you'd be right in saying that this is, solid-like, but something where, like you said, it doesn't have as much rotational or translational degrees of freedom like a crystalline solid would. And these liquid crystals, as the name implies by the liquid part, has a lot more degrees of freedom like a liquid. So these are often, referred to as melting, type transitions. And when you look at them, the most common way is like differential scanning calorimetry as a function of temperature, and it looks at heat flow, which is basically heat capacity. It looks, something like that, and, if this was discontinuous, this would go off to infinity, but, and you get a delta H for that transition, which is that delta H from the, to the liquid crystal. And just like you would get for vaporization or melting, it's probably more associated with delta H of fusion. And you would even say that the range of delta H's you get are they're typically, because they're not truly melting, you're not gaining all the degrees of freedom that a liquid does. It still has the crystalline part
Sure.
there. So that gives you an immediate intuitive feel that these are probably a little smaller than the delta H of fusions, probably not in the tens of kilojoules, maybe less than a kilojoule per mole range, but they still have, significantly heat to, access those degrees of freedom. And these are critical, right? Like that we live in, membranes that have liquid crystalline-like degrees of freedom,
right,
make life possible. Like we don't do very well under gel-like conditions for liquid crystals. Yeah.
Only a few membranes have been found for some insects and things like that that can live in very Arctic conditions, right? And then eventually thaw back out and behave normally.
You brought up a really good thing, and this is directly related to Noka's book, but like you said, what we're looking at in chapter 2, which is basic physical equilibria, this exact kind of gel to liquid crystal transition in membranes gets covered in physical equilibria in chapter 6 for just that reason, that learning the basics of kind of what they saw originally in introductory chemistry courses. One of the reasons we reintroduced that in these more advanced courses is there's such analogies that to really understanding those, to making sure we kind of understand these more complicated transitions.
What would the folding of DNA or a protein model, those tend to not have exactly a gel-like solid state. Could you just say the same thing for folding and unfolding processes?
Right.
That's often referred to in the literature for DNA, at least, as melting.
Well, and they definitely do it when you have double-stranded in it and melt in it, basically dissociates to single-stranded, right?
Right.
That's almost, but like you said, that one famously is called the melting transition, where you lose all the hydrogen bonds and it splits apart. And you would say it's, it's classic, right? Because you can get something about, what the, base pairs must be and how long they are, how many there are, because the melting temperature goes up as you get more and more of those interactions and stuff like that. So, but like you said, proteins have a similar thing. Like you said, kind of the folding, unfolding of a protein, and then we just covered it here. So this exactly, there's a ton of analogy between this quote unquote melting like that we described here as first in a in a lipid. It happens in most lipids, these type of gaining degrees of freedom. And sometimes there's even multiple liquid crystalline phases, pneumatic, symmetric phases, etc. Sure. And then, like you said, or the same type of transition, and it gets even smaller for, a folded protein going to an unfolded protein at high temperature, or like you said, duplex DNA going to single-stranded, DNA melting. And they often call those, they often won't say the folding, unfolding transition. They'll call it the melting type, it's kind of the melting of the protein, or where it denatures or disassociate. They kind of loosely use a lot of terms, and same in nucleic acid chemistry too.
So since those have to do a lot with solvent interactions, can you also think of something that is not even necessarily temperature dependent, where you would have an enthalpy, a change in the delta H term that's based actually on the solvent conditions? I know that you require a lot of ionic strength to fold DNA, for example, screening all those negative backbone charges, probably a lot of proteins as well. We know that we can denature proteins, precipitate them with high salt concentration. So is there something that students should think about in terms of how that would relate to the enthalpy term, at least, or some heat capacity changes with respect to the solvent conditions, since a lot of biological systems that you look at are very complex, so you're not really just thinking about this small set of interactions like you would have between water molecules, right? You have a very complicated system.
The other way I would put that is, oftentimes we take those very simple ideas that we learn on single component systems, like, just the melting of water or ice, of H2O or something, and then we extrapolate them too far, like you said, because like you said, not only is something going from an ordered to a disordered phase, like ice does to liquid water, but what the solvent that it's in, is highly dependent. And if there's other solutes in there, ions that help counterbalance it, or, all sorts of other effects can come in and play small roles where, to first approximation, you rarely see them, or very, very big roles. And I would say that's the good thing about when we cover physical chemistry with a biological focus. We spend a lot of time on, Routes and Henry's law, like basically ideal solute solvent conditions, so how you would expect the solvent to change with different ionic strength of different things, and surface tension effects, and basically just that, because they can be, or doing things in a series of different solvents or ionic strengths, and et cetera, so that you can tease those thermodynamic basically effects out of what is the pure solvent effect, what is maybe a very important effect, an ion-ion type pairing effect, et cetera, by changing the ionic strength, et cetera. And you have to do that, or you're right, you can get very misled, because it isn't, in biological systems, very rarely is it as simple as what we often do really early on in introductory chemistry, which is we think of just entropy as order disorder. We think of enthalpy as just, energy and bonds and stuff. And that very simplistic view helps a lot. And I don't want to discourage students from trying to put things in that term, but at the same time, when it gets more complicated, those break down fairly quickly, and it just gets, you have to think about a lot more interactions and what's really going on, to make some of those work. And it's easy to have them break down. The famous one in protein folding is, you think, okay, like it's folded, takes some energy, just like melting and it unfolds, but there are certain proteins that unfold at low temperatures, that undergo cold denaturization, as they're called. Well, that breaks down from a purely entropy standpoint, you know. So you can't think about things in just as simple of a systems as you did as a single component entropy system anymore.
Definitely with the protein, I would think that you can maybe analogous that to the liquid phase, and that there's some sort of solid phase where it's more of an aggregate, where it's not in its native conformation, or versus something that's the purely unfolded polymer perhaps is more similar to the gas phase. Just in terms of how these things have different degrees of freedom, there's a narrow window for life where you have the right amount of degrees of freedom to have a functional state of something. So.
Yeah, and there is famously even like entropy versus complexity type of things that really play a role here. And then the other one we completely leave out, which is just, you know, we talk about all of this. You mentioned it earlier, reversible. And so as soon as you say reversible thermodynamics, what you're also kind of implying is reversible equilibrium thermodynamics kind of all goes together. And that's almost all we talk about. But paradoxically, given that we live in a non-equilibrium world and stuff, so you know, there's also famously, you know, bringing non-equilibrium at a higher stage gets very important too.
Right. Unfortunately, we need those non-equilibrium effects for life. I think that you can certainly think about the equilibrium effects at a transition state. You know, that Van Hoff is famous for this, right? Where we can take a look at the natural log with equilibrium constant versus the reciprocal temperature. And if you have a linear state, then you can say during that specific transition, you have a temperature independent delta H and delta S value. But you'll find if you actually do these experiments, it's quite a headache. Most of the time, they aren't linear. You have terrible R-squared values of 0.9 or less even for just a simple data set that you collect calorimetrically or spectroscopically. It's actually how we met. I used your calorimeter, your DSC, a couple of years ago to do some of these experiments on DNA, and to my great frustration was not able to obtain any linear values for this type of Van Hoff analysis. So we can say for polymers, at least for some of these things, that non-equilibrium effects dominate even at the transition state. But probably for some simpler systems, like maybe just a liquid crystalline transition, I definitely have seen more concrete enthalpy terms tabulated for those sorts of transitions, you know, in a membrane and things like that. So some of these experiments are fairly straightforward, but you kind of have to consider the interplay of both of them. I think the complexity of the molecule that you're studying, water, you know, is pretty low molecular weight. It may have strong intermolecular forces relative to an ideal gas, but it's still very small versus something that's an entire long polymer chain. So I think the complexity of the system is something that students can use as an inherent guide for, you know, what level of approximation is appropriate, how much they can extrapolate these values from just the solvent by itself, not even the ionic, you know, content of the water, for example. You know, take a lot of caution extrapolating for those things when you have a complicated system.
Yeah, exactly. Well, I appreciate you taking the time today, and hopefully we'll make another video soon.
Great.